Imagine a tool. It was forged back in the 1970s.
Uh-huh.
I mean, it is older than the internet, older than Windows, and almost certainly older than every single student in this course.
No question.
And yet, if you were to just snap your fingers and delete it from existence, the modern digital world would, well, it would just collapse. Your bank records, gone.
The operating system on your phone would be completely bricked.
Even the high-end software they use for CGI in the latest blockbuster movie.
Vanished. It really is the invisible infrastructure of everything we touch. It's not the biggest language anymore, and it is certainly not the safest.
Not at all.
But it is incredibly, dangerously fast.
And today, we are stripping away all the safety rails. We are taking a deep dive into Class 6 of CS330, the Introduction to C.
And it is going to be a bit of a culture shock for some people.
I think shock is probably the intended effect. So, just a quick context check for everyone listening.
Okay.
It is Saturday, January 31st, 2026.
The spring semester is in full swing.
And the mission for this deep dive is to bridge that gap for the student who's, comfortable in the warm, fuzzy embrace of Java or Python and is about to be thrown into the deep end.
The under the hood moment, so to speak.
Exactly. We're going to dissect the lecture notes for the C introduction, look at the syllabus updates, and break down all the logistics. But we have to start with the philosophy. C has been around since 1978, Kernighan and Ritchie. In tech years, that's like the Paleolithic era. Why are we still studying this relic?
Well, because it's not just a relic, it's the foundation. To understand why C even exists, you have to look at the landscape before it. You basically had assembly language.
Right, which is a nightmare.
A total nightmare of specific processor instructions. You're literally moving bits from one hardware register to another by hand.
Tedious, impossible to scale.
Incredibly. And on the other end, you had these high-level languages that were easier to write, but, sluggish and heavy. C was designed to bridge that gap. It was built specifically to create the UNIX operating system. The creators called it economy of expression.
Economy of expression. That sounds very poetic, but looking at these notes, in practice, it feels more like economy of safety.
That is the trade-off. That is the central theme of this entire course, power versus safety.
Right.
If you're coming from Python or Java, you're used to a managed environment. The system creates a sandbox for you. It manages your memory. It cleans up unused objects with garbage collection.
And it stops you from doing anything too reckless.
Exactly. And C is the unmanaged environment.
It's the Wild West.
Completely unmanaged.
Yeah.
C assumes the programmer is smart. It assumes that if you wrote code to access a specific memory address, you didn't make a typo. You meant to do it.
So no garbage collection at all?
None. You allocate memory, you free memory, and if you forget to free it, that's a memory leak, and your program eventually eats all the RAM and crashes the machine.
And what about built-in input and output?
Nope. Everything is a function. Even printing to the screen requires you to import a standard library because the core language doesn't even know what a screen is.
So if Python is a self-driving Tesla that keeps you in the lane, C is a 1960s muscle car. No seatbelts, no airbags, no anti-lock brakes.
But if you know how to drive it, you can redline that engine and go 0 to 60 faster than anything else on the road. It's bare metal.
Let's talk about the actual workflow, because this is usually the first big stumbling block. In Python, you write your script, you type python script.py, and it runs.
The interpreter just reads it line by line.
But C doesn't work like that.
No. C is compiled. You write your source code, let's say hello.c-chi, but that file is just text. The computer can't actually run it. You have to feed it into a compiler. In the notes, they use CC.
For C compiler. Simple enough, .cchello.c.
And this is a big if you have zero syntax errors, the compiler churns out a binary file. By default, it's usually called a .out.
And that file is machine code.
Exactly. Ones and zeros, optimized for your specific processor, and then you run that .out.
It's a two-step dance. Edit, compile, run.
And if you mess up the compile step, you don't even get to try running it.
Okay, let's look at the code itself. The notes give us the classic hello world, and immediately it looks cryptic. It starts with #include stdio.h.
That line trips people up because it looks like a Python import statement, but it's actually much more aggressive. It's a preprocessor instruction.
Preprocessor. So something happens before the compiling.
Precisely. Before the compiler even looks at your code, a separate program scans the file. When it sees #include, it literally grabs the text contents of that library, file-stdio.h, and just copy-pastes it directly into your code.
So it's a brute force find and replace, basically.
That's a good way to put it. Stadio just stands for standard input-output. Since C has no built-in way to talk to the terminal, you have to paste in the manual for how to do it.
And then we hit int main.
The entry point. Every single C program starts at main. And notice the return type is int. It returns an integer.
Which is odd for a hello world. You'd think it just prints and stops. Why return a number?
It's a signal back to the operating system. A return of 0 usually means, success, I finished without exploding.
And anything else is an error code.
Any other number usually indicates some kind of error. You're always communicating with the OS.
Then comes the printing. Printf, not print. Printf.
Print formatted. We can geek out on the F part in a minute, but the key thing to notice here is the N at the end of the string. Printf. Hello world.
And, right, in Python, print adds a new line automatically.
C does nothing automatically. If you don't explicitly tell the cursor to move to the next line with N, it will just sit there at the end of the word world, waiting for the next command.
It really is minimal. Now, speaking of how the code looks, the notes bring up white space. Python enforces indentation. If your spacing is off, the code just breaks.
But C is freeform. The compiler does not care about your indentation. You could write the entire operating system on a single line if you were a masochist.
As long as the semicolons and curly braces are right.
As long as they're in the right spots, it compiles.
That sounds liberating, but I feel like you could tell me it's a trap.
It's a massive trap. This is why the notes emphasize the K&R style, named after Kernighan and Ritchie. Just because the compiler doesn't care about messy code doesn't mean humans won't hate you for it.
Pick a style and use it consistently.
Absolutely. If you hand in code with random indentation, you might get it to run, but good luck debugging it. And good luck getting a good grade. Readability's on you, not the machine.
Let's move on to data types. This is where the danger zone really opens up. The basics are there. Int, float, double, char.
All the primitives.
But there is a glaring omission. I was looking through the notes for the string type, and it's not there.
There is no string type in C.
That just stops people in their tracks.
Yeah.
How do you process text without strings?
You have to build them yourself. In C, a string is just an array of characters. It's a sequence of char data in memory, and this is critical. It's terminated by a special null character. Exactly. So you have to manage the array, and you have to remember to put that null terminator, sort of the period at the end of the sentence, yourself.
And if you forget.
If you forget that null terminator, the computer doesn't know where the string ends. It'll just keep reading memory until it hits a 0 by accident, printing out who knows what. Total garbage.
That leads us to the other major trap, variables and initialization. In Java, if I declare an integer, say int temperature, but I forget to give it a value, Java usually defaults it to 0 or yells at me. What does C do?
C shrugs. If you declare int_var and don't assign it a value, C simply reserves that memory address, but it doesn't clean it.
So whatever was in that memory slot before
is now your variable's value. It could be 0, it could be 5,296, it could be -1,000,000. It's called garbage, and it is a classic rookie bug.
But wait, why wouldn't the language just zero it out for you? It seems so simple to just scrub the memory when you declare the variable.
Because zeroing out memory takes time. It actually takes CPU cycles to write zeros across a block of RAM.
And C prioritizes speed.
Over everything else. It assumes you, the programmer, are smart enough to initialize your own variables. It's not going to waste a single nanosecond doing your chores for you.
That philosophy is just everywhere, even in type coercion. The notes mention passive conversion.
Right. So if you try to shove a floating point number, like 3.9, into an integer variable, C won't throw an error.
What does it do?
It will just truncate it.
Truncate, not round.
Correct. 3.9 just becomes 3. It chops off the decimal. And it does it silently. If you aren't paying close attention, you lose data without ever getting a warning.
Let's look at control flow. The syntax, if while for it all looks, very Java-esque.
Well, C is the grandfather of Java syntax, so the curly braces should feel like home. But there's a really interesting quirk with logic. Standard C has no Boolean type.
No true or false.
Not as keywords, no. In C, the value 0 is false, and literally anything else is true.
So 1 is true.
Yeah.
100 is true.
Yeah.
A -5 is true.
Also true. It allows for some very concise code, but it can be really confusing if you're looking for a Boolean flag and all you find is an integer.
The notes also highlight #define for symbolic constants, like #define upopur300. Why not just make a variable called upar300 equal to 300?
This goes back to that preprocessor we talked about with #include. #define isn't creating a variable in memory, it's a macro. It's just a find and replace command. Before compiling, the preprocessor finds every instance of the word you PPR and swaps it with the text 300.
So it saves memory.
It saves memory because you aren't storing a variable, and it avoids what we call magic numbers, these mysterious values scattered through your code with no explanation. It's a really elegant solution.
Now let's circle back to print and this whole idea of streams. The notes talk about getchar and putchar.
C views all I/O keyboard files, networks, as just a stream of characters. Getchar grabs the next one, putchar spits one out. It's very, very low level.
Okay.
But print builds on top of that to give you this incredible control.
I was looking at the formatting codes. I mean, BRD for integers, sure. But then you have things like person 6.1f.
That's where C really shines. Per 6.1f tells the computer, print a float, but make it take up at least 6 spaces of width and give me exactly 1 digit after the decimal.
In Python, you just print and kind of hope it looks okay. Here, you are practically typesetting the terminal output.
It's crucial for things like the Fahrenheit to Celsius table in the fa2cell.c example program.
Yeah.
If you want your columns to align perfectly, you absolutely need that fixed width.
Okay, we have to talk about the part of the notes that actually scared me.
Ah, yes.
Arrays.
The ultimate speed over safety example, yeah.
Totally. So you declare an array into
All right.
digit 10. You get 10 spots. In Java, if I try to write to index 11,
You get an index out of bounds exception. The program stops cold to prevent damage.
right, a hard stop. And in C,
T says, right away, sir.
it just does it.
It calculates the memory address where index 11 would be, which is just past the end of your array, and it writes the data there anyway.
But what is at that address?
Could be anything. It could be another variable. It could be the return address for your function. You are overwriting memory you don't own.
That sounds like a security nightmare.
It is the definition of a buffer overflow attack. It's how hackers take over systems. But C allows it because checking the bounds takes time.
What do you mean?
Every time you access an array in Java, the computer has to ask, is this index valid? That requires an if statement at the assembly level. C just cuts that check out to run faster.
So if I'm wrong, I corrupt my own program.
Or worse, you create a vulnerability that someone else can exploit.
I am going to be double-checking every single loop condition in Lab 1.
As you should.
Speaking of structure, let's touch on functions. Pass by value.
It's a simple concept, really. When you pass a variable to a function, the function gets a copy of it. If the function changes the value of that copy, the original variable outside is completely untouched.
And prototypes. The notes mention declaring functions before main.
Right, because the compiler reads top to bottom. If you call a function inside main, but the code for that function's at the bottom of the file, the compiler throws a fit. It has no idea what that function is yet.
So prototype is?
It's a one-line heads up at the top of the file. It's you telling the compiler, hey, this function exists, I promise. Here's what it looks like.
A table of contents for the compiler.
Okay.
Okay, we've covered the philosophy and the syntax. Now we need to look at the roadmap. This is a working semester, and these deadlines are tight.
Let's get into logistics. For the students listening, you probably want to have your terminal open for this.
Step 1 is Git. You need to be in your home directory. It's a CD.
Then you need to clone 2 repositories, one for your individual work and one for your team project.
The notes give the specific commands. It's git clone with your username. And for the team, you need that team name. Team best are the one I prefer, the giraffes.
Go with the giraffes. Once you clone those, you need to pull the Lab 1 code. This includes the files we've been talking about, hello.c, fa2cell.c, and digitcounter.c.
Your mission for this week is Lab 1, C Introduction. You're exploring these programs, modifying them, and then writing some new C code.
And do not forget the journal entry. Week 3 is due Sunday, February 8th.
And the 2-1 rule applies here.
Always. Minimum 2 paragraphs, and you must include 1 quiz question based on the material.
Then Lab 1 itself, both the individual and the team parts, is due Monday, February 9th.
There's also a reading on LLMs, 9 habits. You need to do the perusal annotations for that. And speaking of LLMs, there's a specific note about using tools like BitBuddy.
Transparency is the key rule here. The syllabus says you can use these AI tools, but you absolutely have to document it.
Put it right in the re-editing file. I use BitBuddy to explain pointers, or I use it to debug this loop. If you use the tool, you have to admit you use the tool.
So here we are. We're looking at a language that is nearly 50 years old. It has no safety net. It lets you read garbage memory. It lets you overwrite your own stack. Why does it persist?
It persists because nothing else offers that specific blend of simplicity and raw power. C forces you to understand the machine. You can't just be a coder, you have to be an engineer. You have to understand how memory actually works.
It's a difference between driving an automatic and learning to drive stick shift on a racetrack.
Precisely. And that brings us to the thought I want to leave you with. We live in a world that is obsessed with digital safety sandboxes, managed code, guardrails everywhere. In that context, C looks dangerous.
Because it is.
But you should ask yourself this. Is it dangerous because it's broken? Or is it dangerous because it is the only language that really treats you like an adult? If you can master C, you aren't just a user of the computer anymore. You are its master.
Something to think about while you're hunting for that missing semicolon. Check your white space, watch your array bounds, and good luck with Lab 1.
Happy coding.